I want to do another example of drawing a peptide, and we will do this time both drawing it at physiological pH and calculating the isoelectric point. So we did light. Now we're going to do dark. D is the one-letter code for aspartic acid. Which is abbreviated ASP, sometimes called aspartate. And the side chain for aspartic acid is CH2, COOH. A is alanine. Three-letter code is ALA, and the side chain is a CH3. It's the second simplest amino acid after glycine. R is arginine. Abbreviated ARG, because alanine took A, so arginine has to take R, which is the next letter, and aspartic acid can't take S because it's serine, or P because that's already proline, so it ends up taking D just because D hasn't been used. So we'll have D. And then K is lysine. Abbreviated LYS. Arginine and lysine are two of the basic amino acids. In fact, they're the two amino acids that are cleaved adjacent to by trypsin, which is one of your gastric enzymes and recognizes the basic amino acids. Chymotrypsin represents or recognizes the aromatic amino acids, so phenylalanine, tyrosine, and tryptophan. Arginine has a side chain. It has 3 CH2 groups, and then it has a guanidinium group, which is a carbon that's attached to 3 nitrogens. And this group here, this central carbon attached singly to 2 nitrogens and doubly to another nitrogen, is called a guanidinium group. And it's very basic, because if you protonate that, you can get a resonance stabilized ion that's going to stabilize the positive charge over all 3 nitrogens and the adjacent carbon. When you protonate something, it is always the nitrogen that has a double bond to it, as we saw with imidazole. Right? So it's going to be this one that reacts with H+ to give you like that. And now there are many resonance structures that you can draw for that molecule. By moving this pair of electrons around, we can put the negative charge, or the positive charge rather, on the carbon. I'm going to leave off the CH2, 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 and just draw this as R. So we can get a resonance structure that looks like this. Carbon. And now I think you can see that there are lone pairs on all 3 nitrogens, so you could also write a resonance structure that puts a double bond to the other NH2 group. And you could also write a resonance structure that puts that positive charge on the NH group. Because of the great stability of that guanidinium ion with those 4 resonance structures, arginine is the most basic side chain of all, and you will find that the pKa of the acidic function in arginine is 12.5. So this molecule has a pKa of 12.5. Lysine also has a basic side chain. lysine side chain has 4 CH2 groups. And then an NH2. It can also be protonated, but in this case, it's not a resonance stabilized. And pKa of the side chain for lysine is equal to 10.5. So a better acid than the protonated form of arginine, the guanidinium ion. Therefore, right, since that's a stronger acid, lysine is the weaker base. This is a weaker base than guanidine because the positive charge can't be stabilized by resonance. So we know what our side chains look like now. In this case, there are no chiral centers in any of our side chains, so we don't have to worry about that. But 3 of the 4 side chains in dark do involve something that can either be in its protonated or its deprotonated form. So this is asp-ala-arg-lys, or aspartyl, alanyl, arginyl, lysine as the peptide. And as usual, we will draw it with everything protonated to begin with. And we will be alternating between pointing up and pointing down as we go from one to the next. So our first amino acid is pointing up, our second amino acid, alanine, will be pointing down, our third amino acid, arginine, will be pointing up, and our fourth amino acid will be pointing down. We'll leave the carboxy terminal protonated. We'll protonate the N terminus. Right? Aspartic acid is going to have that CH2, COOH, and we'll leave it protonated for now. Move that a little bit so I can show the bond to hydrogen. This hydrogen is coming out, which means the CH3 group is going back. Here we have the hydrogen going back, and then we have CH2, 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 NH, C, NH2, positive charge, another NH2, that protonated guanidinium group, and then on lysine we have the hydrogen coming up. And we have CH2, 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 NH3 plus in its protonated form. So we have the N terminus of aspartic acid. We have the aspartic acid side chain. We have the guanidinium side chain of arginine. We have the protonated amine side chain of aspartic acid, of lysine, and we have the C terminus of lysine. So we actually have 5 acidic functional groups here. And we have a net charge of positive 3. For the fully protonated peptide. And we can look up the pKa values. So the aspartic acid N terminus has a pKa of 9.6, and the side chain has a pKa of 3.7. The C terminus for lysine has a pKa of 2.2, and the acidic function here, the side chain, has pKa of 10.5. And finally, the side chain of arginine, we already know has a pKa of 12.5. Five acidic functional groups. 5 different pKa values. You'll notice that the pKa of the carboxylic acid and amino acids is always around 2-ish. And that's because of the electron withdrawing nitrogen in the adjacent position. That electron withdrawing inductive effect is going to increase the acidity, decrease the pKa by about 3 orders of magnitude. Even here, this side chain is close enough to that NH3+ that the pKa of the side chain is also significantly lower than the 5 we normally use for our standard amino acid. If we wanted to draw this amino acid at physiological pH, all of the side chains that are less, whose pKa is less than the physiological pH of 7.4 will be deprotonated, which means the 2-carboxylic acid functions, and all of the pKa values that are greater than physiological pH of 7.4 will be protonated. So 9.6, 10.5, and 12.5 will all be still in their NH3+ or NH2+ version. So at physiological pH, we would draw this slightly differently. We would draw H3N+, COO- here. This would be protonated, this would be the NH3+, and this would be a COO-, right? So we'd have 2 minus charges in there, and at physiological pH, that would mean that the net charge on this molecule would be +1. And I'll draw that shortly. For the purposes of calculating the isoelectric point, we now have to figure out which of these 2 pKa values are going to be on either side of the neutral species. So we start with our net +3 charge, and that's going to be in equilibrium with something that has a +2 charge and a hydrogen ion, and we know that that pKa, pK1, is the most acidic pKa we have of 2.2. The +2 species will lose a second proton to become a +1 species, and A+, and pKa2 is equal to 3.7. The +1 species can then lose another one, become neutral species, and H+, pKa3 is going to be 9.6. The neutral species can then lose another one to become -1 species, and hydrogen ion and pKa4 will be equal to 10.5. And finally, that -1 species could lose another hydrogen to become -2 species, and hydrogen ion, pKa5 is equal to 12.5. So we can go all the way from +3 with all 3 of our nitrogens protonated to -2 with both of the carboxylate groups, deprotonated carboxylate groups instead of carboxylic acids. The 2 we need for the isoelectric point calculation are these 2, the 2 that involve the +1 species. So when we are looking for our isoelectric point, we're only worried about the N-terminus of aspartic acid and the side chain of lysine. Those are the 2 pKa's that are on either side of our neutral species. So to calculate our isoelectric point, we take the 2 pKa values on either side, and it's going to be pKa3 plus pKa4 divided by 2, the average of those 2, which is equal to 9.6 plus 10.5 over 2. That's equal to 20.1 over 2. So the isoelectric point in this case is equal to 10.05. Significantly more basic, right? The pH of 10.05 is where the isoelectric point, or where the species is net electrically neutral. That's significantly more basic than the previous one we did, light. So dark is more basic than light, and that would make sense because it has 2 highly basic side chains, as opposed to the other one, which had a slightly acidic side chain, the histidine with a pK of 6.1. At physiological pH, we would want to draw our peptide like this. 9.6 is above 7.4, so that one would stay protonated. deprotonated though, because the pKa of 3.7 is less than physiological pH of 7.4. So alanine doesn't care. No side chain there. The arginine side chain stay protonated. This 12.5 is certainly higher than 7.4. The carboxy terminus would be deprotonated. Lysine side chain would stay protonated. So we have 3 positive charges in the molecule and 2 negative charges. The net charge at physiological pH of 7.4 is equal to +1. One more protonated nitrogen than there are deprotonated carboxylic acids. So it would be this one. The one in the middle. At physiological pH of 7.4, all the functional groups with pKa higher than 7.4, which is the N-terminus, the side chain of lysine, and the side chain of arginine are protonated, and all the functional groups that have pKa less than 7.4 are deprotonated, which would be the side chain of aspartic acid and the C-terminus of the lysine. So on the final exam, I'll give you a short peptide and ask you to draw it, both as it would exist at physiological pH, and then I will ask you to calculate the isoelectric point by finding the 2 pKa values that are on either side of the neutral species, and then averaging those. And I'll probably ask you to derive the equation that allows you to know that the isoelectric point is simply the average of the 2 pKa values on either side of the neutral species. That derivation is shown in the printed lecture notes.